My guest today is Kesten Green.
Tom, I've got a talk for us about a very recent paper that I published with Willie Soon, who your listeners will be familiar with. This is the latest in a series of works, but three academic papers, major academic papers over the years since about 2007, 2008, that I've written on climate forecasting. Starting with my good friend and colleague, unfortunately now deceased, Scott Armstrong, who is a founder of the International Institute of Forecasters, the International Symposium of Forecasting, the International Journal of Forecasting, and wrote key works in the forecasting canon. So that's my background is in my academic life. Before that, I was in business for several decades, but I became addicted to doing scientific research on forecasting. And back in 2007 or so, we were looking for a topic for a talk for the International Symposium on Forecasting. And I said to Scott, well, I'm not sure that these people who are the IPCC people who are making these forecasts of dangerous man-made global warming really know anything about forecasting. So I think we should have a look at that and see what we find. And so Scott and I set out to do a forecasting principles audit, if you like, on the processes, the procedures, the methods that were being used to put together the forecasts that the IPCC were publishing, the dangerous man-made global warming projections. And we found that they violated almost every principle of forecasting that had been identified by scientific research over decades and decades. And after giving the conference paper, we published an academic paper on that, summarizing that evidence. And we thought it was done and dusted, really. We thought we'd made an original contribution that was different from the angle that others were taking. The physical scientists arguing about the details of the causal mechanisms and the feedbacks and so on. We looked at it from a scientific forecasting point of view and said, well, there's no basis for believing that temperatures are going to go up over the longer term any more than there is to go down. But that wasn't the end of it, as we know. Nearly 20 years later, and a couple of years after that original paper, we got in touch with Willie Soon to look at making some or testing the validity of the forecasts as a time series exercise. As a 3 degrees centigrade per century, a good forecast compared to alternatives such as no change from the average historical temperature. And when we found, well, actually no change from the historical temperature works very, very well, and most of the time is more accurate than the 3 degrees Celsius of warming that is supposed to be occurring due to human activity. And again, Scott and I anyway thought, well, this is done and dusted, really. What have they got left to go on? Well, the stories continued. Our work was largely ignored, and so here we go round again with a different look at the forecasting problem. This time concerning ourselves with the modelling of the physical processes, and we take a scientific approach. We're using the scientific method, which is concerned with testing alternative reasonable hypotheses. Well, you can see on the slide in the image behind me on the screen that that Scott and I published, shortly before his death, a book called The Scientific Method, where we provide checklists and much summary and history of the use of the scientific method and what's going wrong with it. Well, key component, as I say, of the scientific method is testing alternative reasonable hypotheses, and that's what we're doing here. Back to the question of, should we trust the UN, IPCC, International Panel on Climate Change, Intergovernmental Panel on Climate Change, climate model forecasts? And our answer from the scientific method. So I understand that some of your viewers, listeners have limited time, so I'm going to summarize it in one slide up front for you in brief. And in one sentence, net zero makes no sense. Why is that? Well, the IPCC climate models predict dangerous man-made global warming from human emissions of CO2. We call them anthro in the course of this paper. And they can claim that the radiation from the sun doesn't cause or did not cause variations in temperature from 1850 on, when most of their data is based. But that's based on their own choice of a total solar irradiance variable. Let's call that IPCC solar. IPCC solar didn't vary over the historical period that we're looking at through to 2018, when we've got the available data. Hardly varied at all. We'll see charts of that during the talk. But there are 27 other measures of solar variation, all with respectable attempts to measure this. And some of them varied considerably. And so we, in the course of this paper, tested alternative causal hypotheses, and we could call them H1 and H2. The IPCC models, H1 is the IPCC's anthro variable, essentially CO2 plus volcanic. The volcanic variable, the volcanic emissions variable, is in all the models, so I won't mention that again. The H2 model with the red there includes the IPCC solar variable, which they say isn't important, and we'll see why they don't think it is in the talk. And the other two, H3 and H4, don't use the anthro variable. They use, but they do, instead of anthro, use independent solar variables. And independent as in ones that weren't chosen by the IPCC. And the fifth hypothesis, which is sort of our benchmark hypothesis, is a no-change model, which says let's calculate the median of the temperatures in our estimation sample and use that median temperature as the forecast for the out-of-sample data temperatures. And what we found was that the accuracy of the IPCC model forecasts varied greatly depending on what data we use to estimate it. This is rather strange, given that they're causal models and your physical causal relationships. We should expect them to be the same no matter how the what set of data data we use. Think of the most basic, one of the earliest examples of plotting a causal relationship of the heights of fathers against heights of sons. We expect broadly as the height of the father is taller, the height of the son as a grown man is also taller, and vice versa. We don't expect one sample of fathers and sons to have an opposite relationship. Okay. So to support that causal reasoning, what's reasonable in causal relationships, the independent solar variables and the no change forecast didn't behave in this strange way using different samples of the data. Moreover, the IPCC anthro forecasts were mostly much less accurate than the alternative solar, and most of the time, depending on the samples, we use less accurate than the median temperature. So the models, the anthro models, are unreliable. They lack predictive validity, to use the technical term, and so I think we can reasonably conclude that the anthro variable that the IPCC have created is not a credible causal variable. And read again, when CO2 isn't shown to and by any of the evidence to actually do anything to temperatures, it fails to be a valid predictive variable, then attempts to change are going to not produce any benefit, and will instead produce the poisonous fruit of expensive energy wasted and misallocated resources. So there we have it in brief. So for those of you who are interested in perhaps testing my thinking, examining it a bit more closely, and looking at the evidence that Willie and I have produced in this paper, let's move on to the next slide. Oh, and there we are. So there's the paper, which a link, and with a link, the name of the paper that we've written, and the reference for it. And I understand Tom will make this available, the slides available to you, and then therefore the link to the paper itself. So, background. The IPCC rejects a substantive contribution of the sun to increasing temperatures since 1970, and they base that on what they call attribution studies. So what do we mean, or what do they mean by attribution studies? Well, let's go back to that. What do they mean by attribution studies? They mean that they have constructed a temperature series, a global average temperature series, or various regional temperature series from observational data that they manipulate, massage, and I think the term is homogenize, and then they look for reasons why that has changed. And the reason that they're primarily looking for, because that is the brief they have been given, the UN IPCC was set up to look for human effects on climate. So, of course, that's what they're going to be looking for. And to that end, they constructed this anthropogenic variable, man-made, human-caused, principally CO2, and they have looked at some of the solar variables and the anthropogenic, and then they say, well, the solar isn't doing anything. Well, Willie Soon, along with the Connellys and many others, published this paper in 2023 with a rather technical title, Challenges in the Detection and Attribution of Northern Hemisphere Surface Temperature Trends since 1850. And what did they do? They compared the statistical fits. For those of you who are familiar with statistics, R squareds, adjusted R squareds, or multiple correlation coefficients is another term, of causal models of 5 measures of the Northern Hemisphere surface temperature. So 5 measures. We're going to look at 2 in this paper here, but okay. So they looked at the statistical fit for models of 5 different measures of the temperature, alternative hypotheses about what the temperatures were, and they estimated models. 275 models, in fact, using putative, assumed causal variables and measured in watts per square meter. So each of the causal variables was converted into this watts per square meter measure of energy power. So among those models, well, they tested 28 different solar variables, including the one that the IPCC preferred. They had some of the models that didn't include solar at all, and they used the IPCC's volcanic variable or not, and the IPCC's critically their all anthropogenic variable or not. So a lot of models, a lot of alternatives, and their conclusion was that the statistical figures were consistent with temperatures being mostly human-caused, mostly natural, or some combination of both. Well, this is quite a different story to the mostly human cause that, in fact, almost entirely human cause that the IPCC have settled on. Now, I'm a forecasting scientist, and one of the things that we know is that statistical fit tells us very little about predictive validity. So when I saw this paper, I thought, well, here's an opportunity. Willie and the Connellys and colleagues have gone to all this trouble to put together all this data. I can take at least some of these models and look at the idea of predictive validity. And so this is what we're addressing here in this next slide. Do any of the models provide useful forecasts? So what do we mean by that? Useful forecasts, and we're talking about predictive validity. It's one of the key tests of a scientific hypothesis. Does the hypothesis, in our case model, predict data that the hypothesis, when it was, or whoever generated the hypothesis, didn't know about when it was generated? In this case, when we're talking about models, can a model that's estimated on one set of data to express a hypothesis about a causal relationship, how does that hypothesis in the form of a model go at predicting data that it didn't know about when it was estimated? predictive validity. And how do we judge whether a particular model is has predictive validity? Is in our case is a 1 degree centigrade error a good thing or a bad thing? Is a 5 degree error good or bad? Well, we want to have some kind of benchmark, some kind of basic model that we can test against. The hypothesis isn't much good if it doesn't at least do better than a simple alternative. And this is the point I made earlier. We know from forecasting research that the relationship between statistical fit, which is what the Connellys and Willie and co had looked at, doesn't answer that question. It certainly raised the question as to whether the IPCC had any real claim to have a valid model, but it didn't answer the question. And just a technical note here is that although we estimate models using one set of data to predict temperatures that weren't included in the estimation process, that we use the known values or estimated values of the causal variables to do that. We don't try to forecast solar, anthro, or volcanic as an independent exercise. So in some senses, it's a relatively easy test of the models. So the other aspect that we're interested in useful forecasts is the idea of reliability. So if we estimate the relationship, the causal relationship on one set of data, do we get the same or very similar model to estimating it on another set of data? So, do any of the models provide independent for model coefficients, model relationships that are consistent, independent of the sample of data that's used to estimate the model? And it's thinking about this. Well, what will one expect of one test of reliability, of the accuracy, in other words, errors of the forecasts, if the model were valid, as more data is added to the estimation sample. So if you might start thinking from a historical point of view. Maybe we've got the first 50 years of data and estimate a model, and then make forecasts for a period in the future. Those forecasts will all have errors, greater or smaller. Now, overall, what will we expect to happen to the size of those errors as we added extra data? So, we add extra observations from 1901, re-estimate the model, make the forecasts again. Are those forecasts going to be more or less accurate? Add another 5 years, another 10 years. Should the forecast be getting more or less accurate as we add, more data? And this is gives us an indication of the reliability. So, to answer my own question, what we'd expect is that as we add more, data to estimating our causal relationship, we should find that there is more. We get smaller errors. Our forecasts become more accurate. Our model becomes a more realistic representation of the causal relationship. Okay, so and then the Connellys and Willie's study. They looked at northern hemisphere temperatures. Why did they do that? Well, it's all to do with, that's where the data is. And we can see from the 2 or 3 different images there, where the weather stations are, where the measurements were. Almost all on land, but overwhelmingly in the northern hemisphere, and with longer histories. So that's why. So rather than, well, I don't think I need to elaborate on that. The IPCC's anthropogenic and volcanic variables, what's the nature of those? Well, their anthro variable is a variable intended to represent the hypothesized human impact on the Earth's temperature. So it's a composite of 11 proposed influences from anthropogenic, man-made influences. It is mostly human emissions of CO2 into the atmosphere, overwhelmingly so. And volcanic eruptions affect the amount of heat escaping from and arriving on the Earth's surface, depending on the nature of the eruption, whether it's an undersea volcano and lots of water vapor, or a surface volcano and lots of ash and dust. And so the IPCC have constructed a historical series on that, which we use in all the models as well. But we don't use the anthro in our ones. And finally, the other IPCC model that we look at is their solar model, total solar insolation, irradiance. And you can see that the 3 of their variables there from left to right, well, that anthropogenic variable over time is the horizontal axis, and the vertical axis is the watts per square meter. And it seems that the CO2 wasn't doing anything until about 1970, and then all of a sudden it had a huge impact in terms of watts per square meter. Volcanic forcing, we've got some substantial downward spikes that coincide with major eruptions. But when we look at their solar variable, their preferred solar variable on the same scale, well, what's going on there? Not very much, is it? We'll be looking at that in a number of different ways in some future charts. But well, no wonder they couldn't find any relationship, and also with the anthro variable that they used, no wonder that seems so important to them. Okay, what about the alternatives? Alternative total solar irradiance variables. IPCC's solar, just going back to that, from their AR6 report, uses Mathis et al.'s 2017 estimate, and as we've just seen, it's a low variability estimate. We're scientists, so we test alternative hypotheses, and these are the 2 solar variables that of the other 27 that we chose to test in this predictive validity test in our paper, and they're both high variability relative to the IPCC solar variables. The first one, Bard et al. 2000, 11th largest range of the 27 or 28, and it has the smallest correlation with the IPCC's solar variable. But you can see even the smallest correlation is a non-trivial 0.39, where 0 means no correlation and then 1 means perfect correlation. And the second of them has a correlation of 0.62. But it also has a much larger range. It's had the second highest, or has the second highest range in watts per square metre of the solar variables. And interestingly, and finally, the H1993 solar variable was endorsed in the earlier IPCC AR4 report, but was subsequently dropped in the most recent report. Why is that, I wonder? Well, we're not going to answer that question directly, but perhaps the following slides from our findings will address that. So here are the 8 models that we tested in the study, not including the benchmark model. So let's just have a look at over on the right here. We've got the variable we want to forecast with a bit of graphics there. So the one on the brown and the orange background, we're talking about the northern hemisphere, all land annual average temperature anomaly. So all land, we've got a symbol of the and includes cities and built up areas as well as rural. And the second variable that we want to forecast is just the rural temperature anomalies only. And we'll talk a bit about why we want to have a look at that in a moment on the next slide or two. So those are the temperature series we want to forecast. The individual models, we use 4 different models to forecast each of them, and the causal variables are the same between the we've got four models with 4 different groups of causal variables, each forecasting 2 different temperatures. So let's go through them in order. The first model is the, if you like, preferred IPCC model. Looking at the first line on the left, it includes the anthropogenic variable from the IPCC and their volcanic variable. The second model is another IPCC originated causal model, but this time we've included their solar variable. And then the subsequent 2 are the 2 independent solar models, B2000 and H1993, after the names of the solar variable or the authors of the solar variables, and then they all include volcanic. So we don't need to talk any more about that. And as I say, the next 4 are the same, but they're the same causal variables being used to forecast rural-only temperatures. So we use the term independent to indicate solar models that use variables that are not the ones used by the IPCC, and they do not use the IPCC's anthro, human-caused variable. So, urban heat island effect. Why are we interested in rural? Willie provided this from, I think it may have been a talk he gave to you. Boy, it's dramatic. So on the left, we've got a temperature chart, August 28th, 2018. High summer in Washington, D.C., and we see a range of temperature over 17 degrees Fahrenheit color-coded there. That's extraordinary. And so what are the bright orangey reds and what are the dark blues? Well, if we go to the right, we can see the satellite image that shows the deep blue areas are areas of forest and riparian parkland and so on, whereas the dark orangey red areas are the built-up areas, what we call urban heat islands. And boy, that's a major difference. Well, the urban heat islands aren't caused by CO2 in the atmosphere. They are caused by local effects like running machinery, vehicles, air conditioning units, factories generating heat, lots of black asphalt and concrete and so on that absorbs and re-emits heat. So any model, really, if we're looking for what causes changes in the Earth's temperature, ideally we want to be getting rid of those kind of local effects and Willie and the Conleys and so on did putting together their data series was put together a rural-only series that as an attempt to better represent, the real temperatures of the Earth rather than local heat island effects. So we shall, compare the two all the way, through and see what we think. So these next few charts represent or show the assumed causal relationships. They're an XY chart for those who are familiar with the jargon. So the horizontal axis is watts per square meter, and the vertical axis is degrees Celsius. So we're talking about changes in the assumed causal variable in watts per square meter on the horizontal, and the variable we're wanting to forecast in degrees Celsius on the vertical axis. And what we've got here is the all land temperatures. So we do include we've got the urban temperatures in here, and we're looking at the period from 1850 to 1969. Okay, so the top chart is the anthro variable in watts per square meter on the horizontal axis, and how does that relate to the temperature variable on the vertical axis? Well, as we saw in the earlier representation, there's not a lot of change in the anthro over this period of time up to 1969. There's nothing much happening there, despite the temperature of all land changing. Well, what is that? About degree and a half or so from high to low, and similarly with solar, there's even less change in watts per square meter, and yet the temperature's changing. Okay, so no change in solar, no change to speak of in anthro, and yet the temperature's changing over this range. What about when we look at rural? Sorry, no, we're not going to look at rural yet. We're going to bring in the 1970 data, and we've got those coloured in red. So the data from 1970 to 2018 is in red. Well, when we look at the top right chart this time, we see that after 1970, we have something that looks like a causal relationship. The anthro variable, changes. More, what are we looking at? At about 3 watts from the low to high there. And temperatures change, well, again, temperatures over that 1970 to 2018 period, change about the same, maybe a little bit more than they did over the earlier period, the 1850 to 2018 period. So what's happened? This seems to be a causal relationship that is very different or almost non-existent prior to 1970, and then all of a sudden looks like what you'd expect from a causal relationship, a positive causal relationship. The solar variable, the bottom right one, we'll look at now, and notice that as we'd expect from the earlier charts, it just doesn't change in terms of the amount of energy effect as measured by the preferred IPCC variable. In fact, if you really want to look closely, the relationship is negative after 1970. So in other words, more solar activity, more solar irradiance, according to the IPCC's solar variable, leads to lower temperatures. Okay, you have to look pretty closely to see that. So now contrast that with the two independent solar variables. And particularly with the bottom one, the H1993 solar, which was actually the one that IPCC had looked at favourably in earlier reports. They're broadly what you'd expect of a causal relationship, a positive causal relationship, upward sloping from left to right, more watts per square metre, higher temperature. And if we add in the 1970 onwards data, well, same again, really. We're looking at, they're a bit messy. Why? Well, there are other things that cause changes in temperature other than just the single variable, but, broadly they're what one would expect to find from a causal variable. Okay, let's have a look at the rural, and we'll do this just quickly because although the spread of temperatures is greater, the picture that we see is not dramatically different in terms of the basics of the relationships or lack of them. Okay, so there we go. And reinforces that the rural temperatures aren't when rural temperatures went up, then they also went up or down when urban temperatures went up or down, but not quite the same way or to the same extent. So I mentioned early on the need to have a sensible benchmark, although we've got quite a few hypotheses going on here. Perhaps you could argue that we didn't need one, but it's always good good science, especially in forecasting, to have a very simple model to compare with. Well, the one that we've used in this paper is the median temperature of the estimation sample. And why have we done that? Well, as I wrote in my 2015 paper on simplicity versus complexity in forecasting, the evidence falls very heavily in favour of the simpler methods. wherever we could find tests that compared a complex proposed new forecasting method with a simpler one, a reasonable simpler one. We found that the simpler one was as or more, provided as or more accurate forecasts. And it's also consistent with the forecasting principle of conservatism, or sticking close to what we know, not predicting that the future will be different from the past. And certainly physical scientists should appreciate that idea. You don't predict that the apple's going to fall up in the future when it's fallen down for as long as we know, and in every experiment we're aware of. This also relates to realism, the conservatism, idea that what we know from inspecting temperature estimates of temperatures over long periods of time on all time scales, going back into geological time as well as more human time scales, is that the apparent trends, we can see apparent trends all over the place, and you can construct, you can conclude there's a trend in whatever direction you like, depending on your starting and ending point. But those apparent trends will reverse on all time scales, whether it's on days or years or centuries. So, but also an issue that we've got in forecasting climate, in this case particularly global temperatures, is that the assumed, the putative causal variables are difficult, if not impossible, to forecast accurately. There've certainly been attempts to make predictions about solar irradiance, but I've yet to see anything that is convincingly predictive. And also, over time periods of human interest in particular, and more especially volcanic, which can make as we know, enormous differences to temperature on Earth. Including throwing us into a new ice age if the volcano's big enough. So if we can't predict those, then we've got problems with causal models, and we may not be able to do any better than a simple average or the most recent figure. Realism. And in the prior evidence from my previous paper with Scott and Willie in 2009, the benchmark we used there was the mean historical figure, and that performed better than the IPCC's 3 degrees centigrade per century. All right, here's some results. Okay, let's start slowly with the first one. So we're looking at absolute errors, so irrespective of direction. So it's it could be plus 1 degree Celsius or minus 1 degree Celsius difference between the forecast and the measured value. We don't care. We're just interested in the size of the error, not the direction of the error here. So the vertical axis of the chart is in degrees centigrade. So they all go up to 6 degrees centigrade, and they start at 0, no error. Well, we get pretty close to 0 error, there at the beginning of these charts. So what are the horizontal chart shows time and years. So what we're doing here is we're looking at the forecasts going out from 1900. We've estimated models, as shown in the red underlining there, using data from 1850 to 1899. Okay, so there's 50 years of historical data of data that we've used. It shouldn't matter what set of data we use, and we'll be doing some different tests again in a minute. But in this case, we're looking at a sort of a historical representation. If you were sitting in 1900, using the data that was known at the time, and forecast out to the end of the period that we're looking at, 2018, this chart shows the size of the errors in degrees Celsius of the 5 different models, including the median historical one. So on the left here, the chart we're seeing at the moment is models forecasting the all land temperature, which, remember, includes the urban heat islands in there. And what we can see is with the color-coded lines that as we get further and further away, further and further out, or rather when we get into the 1970, whoops, I didn't want that yet. And when we get beyond about 1970, the errors of the models, other than the IPCC ones, get larger. They head up towards about 1.5 to 2 degrees centigrade, whereas the IPCC models, the red and the black lines, they increase a bit, but they stay down around below that 1 degree centigrade. Okay, so where are we going? Where are we going here? Well, let's look at what difference rural makes, because remember, this is where they depart is around 1970. So let's have a look at what happens if we estimate the models to forecast rural-only land, and we get this chart, and we get a very, very different picture. I've had to insert an extra little bit of chart there that with the red and the black line goes from the 6 degrees up to 21 degrees. Okay, those errors explode. Well, even quite early on, we're looking at forecasts through the 1920s and right through to the beginning of the 60s. The errors are 2.5 degrees or so. Then they settled that back down again to about 1, and then explode off for forecasting, rural temperatures without the urban heat island effect. Whereas, let's go back to the independent models, the blue and the green. They trickle along, and the errors don't really get that much bigger. So, that's suggesting that they're modeling with the data from 1850 to 1899, they are estimating a valid relationship that holds all the way out to 2018. Okay, whereas the IPCC figures don't. There's something different about what's going on with the causal relationships beyond about 1920 or so. Why would that be? Well, I can't answer that question directly. One can speculate. Let's have a look at some more examples. Let's step forward in time now and say, okay, now we've got some more data. We've got 100 years of data, and we're going to forecast from there from 1950 out to 2018 when our data series ends. Well, this is a bit strange because we've added more data to estimating our models. And for the all land, we've now find that the IPCC models, the red and the black overlap each other here, explode away around 1980 or so in terms of the errors they're making. So by 2018, the errors of the forecasts are up to 4 degrees centigrade. Whereas the alternative models and the median figure trickle along well below 1 degree centigrade for most of it, and then dribble up above 1 degree centigrade in 2018 or so. What about rural? Well, it's even more stark there. The independent models and the median benchmark, stay down. Even the median benchmark is below 1.5 degrees centigrade out at 2018. The independent models are almost entirely less than half a degree, sometimes getting up to about a degree, at most, for some of those years. And again, stepping forward in time, similar picture when we've got now, how many years is that? 120 odd years of data to this 1970 point. Again, the independent models and the median figure are doing well, even for the all land, and dramatically better for the rural land without the heat island effect. But finally, when we've got all the data, well, not all the data, we've got data through to 1999, so we've got 150 years of data, and we're just forecasting 18, 19 years of out data, of data that the models didn't know about. And we find that the IPCC forecasts have got very, very small errors here. The independent models and the median model, the benchmark model, still respectable figures, but for some reason the anthro models, the IPCC models, forecasts seem to be magically accurate. And that's even the case with the rural land forecasts. Preternaturally, is it the right word? Accurate, preternaturally. So there we go. So the independent models have been very consistent in their level of accuracy, particularly for the rural land. But we've seen some very strange behaviour in the accuracy of the forecasts of the IPCC forecasts. Now, this is I don't want to dwell on this. This is for completeness. I'm just showing an error, one of the error measures that I use in the next slide, which is a useful, relative error measure. It measures the error relative to the benchmark of the models, model forecasts. So let's have a look at the relationship between predictive validity and statistical fit, which is what excited me in the first place, because I thought, well, we can do better on this topic. And what is the relationship? And consistently with forecasting, research, we find little relationship, but in this case, the relationship so little, it's worse than little, it's negative. So Going to the second bullet point, the summary there is the R squared as the statistical fit increases, the forecast accuracy decreases. Oh dear, and a few qualifiers there. I mean, looking at the 8 different models, that correlation was large and negative for 5 out of the 8 combinations of estimation period and temperature series that we wanted to forecast. And only one of the combinations, one of the 8 combinations, which was all land models estimated with the largest sample size, was the relationship large and positive. So it's not it's the opposite of an endorsement of choosing models on the basis of statistical fit. Not good forecasting principles. Plenty of evidence to show that that's the case. And that's very much what has been done with the justification for IPCC models and most other models that are used for forecasting and making claims about knowledge. Now, this one starts to get a bit complicated. So let's go through the title. So we're looking at the reliability now of the models, and we're starting off with the no change model, the sample median, the yellow line, and what we've got is what we're showing on the vertical axis is the median absolute error of the Northern Hemisphere temperature forecasts between 2000 and 2018. So in other words, for all these charts that we're going to be looking at now, we're looking at forecasts for that period, and we're looking at the median absolute error, the middle absolute error of forecasts made for that 19-year period. So back to the chart and look at the horizontal axis. And what the horizontal axis says is it's got dates on the very bottom of the horizontal axis label, and it's got above that, immediately below the chart, it's got the number of observations in the estimation sample, so which ranges from 50 for models estimated in using data up to 1899, 100 and for models estimated up to 1949, and so on. So what we see with the benchmark, the estimation sample median, the yellow line, behaves as we'd expect. The more data in the sample, the smaller the error gets, the smaller the average error for those forecasts for those 19 years of the 21st century. Okay, very well behaved, very reliable, using the median temperature in the estimation sample. So that's one I've got on the screen at the moment is all land temperature, and on the right, rural land temperature, even better. It starts with a smaller error. The error gets almost monotonically smaller the more data we add to our estimate of the median. So let's now go and add the other series in and see how they perform. So now we've added in the independent solar models, and you can see that the green one, actually the errors are a bit larger than the median for a while, but they get smaller and smaller as we add more data. Similarly with the blue, which is a bit more a bit better behaved, and it behaves as you'd expect. More data, smaller errors. More data, smaller errors. Same again, but better with the rural. At some point there, the green line for the rural is pretty much bottoming out at almost zero, which suggests that the causal relationship is remaining stable. Doesn't matter what data you add to it. More data you add, it gets a little bit more refined. But at some point you've got enough data to have a good fix on the relationship, and the error reduces to a level that's not going to reduce much more, or if at all. Now let's have a look at the Anthro model. Without the IPCC solar. It looks a bit sketchy because I've been a bit lazy as to how I generated the charts. I've actually hidden the other series rather than drawn a whole lot of new charts. We'll see it more clearly in the subsequent ones. But there we are. So there's the Anthro and volcanic. Well, that doesn't. Again, we're adding more data to forecast those same 21st century temperatures, and it's only when we add the last few years that the error reduces, and it reduces more than the other models. But most of the time, it's estimating. Well, the relationship it's estimating can't be is unstable, or the series don't actually represent a valid causal relationship. When we look at rural temperatures, it starts to get really scary. When we see those errors going up to 17 degrees, when we have got 50 observations to estimate the model we're using to forecast 21st century temperatures, reduces and reduces and reduces, and then explodes out again to 4 degrees centigrade before dropping back down again. This is not what we would expect from a valid causal relationship. When you add more data, it should be getting better at estimating it, not be all over the place. And finally we add in the Anthro with the volcanic and the IPCC solar, the red line, and because as we know, IPCC solar doesn't really have any effect. They're pretty contiguous lines there, similar picture. Something deeply strange going on. This one, I won't dwell on this chart, this table too much, but this is another approach to looking at the reliability, the idea that of comparing estimates of estimating models on the first half of the data to forecast the second half of the data, to estimating models using every first observation, every odd observation. I think is the way I've done it, in order to forecast every even yeared observation. Okay, well, again, two samples of the same size, if the causal relationship is stable, shouldn't make a lot of difference. Although you could reason that by including a longer, a broader sample over a greater period of human history, then it was going to be more representative. So we'd expect some improvement in accuracy from using every second observation rather than the first half to forecast the second. Let's have a look at some notes on this, and I'll talk a little bit about it. So, models estimated using 84 consecutive years of data versus models estimated using 84 years of odd years data. What's the difference? What happens there? Well, the IPCC models, the reduction in the median absolute error is quite considerable, and the reduction in the interquartile range, the spread of the errors is quite considerable. Whereas the independent models, it doesn't make a lot of difference whether you use the every second observation to estimate the model or the first half of the data set. So again, this is supporting the idea that if a valid causal relationship shouldn't be different depending on what set of data you use. So let's have a look at so the red figures there show that for on the top left there, the northern hemisphere all land errors for the anthro and the anthro with the IPCC solar, they're smaller than the independent ones when you're using consecutive years of data. So in other words, time, the particular set of data that you use, makes a difference. The IPCC models essentially need a representation of all the data in order to perform well. But even so, if you look at the adjacent red figures, the interquartile ranges, the interquartile ranges for the anthro models are considerably larger. They're about double the size. So less. Even with a preferred set of data in terms of the average absolute errors, the median absolute errors, the reliability of those forecasts is nowhere near as good. Now you look at the right-hand block of data for rural land and the top right set of red figures, and you'll see there quite clearly, as we'd expect from what we've seen before, that the errors of the independent models are about half those of the anthro models, the IPCC models, on average, and the interquartile range is about a third. So the size, the spread of errors, the reliability of the forecast is much better. Well, the bottom chart just shows the ratios to emphasize that it doesn't make a lot of difference which set of data you use if you're looking at rural temperatures and the independent models. Which are looking at the what happens to the coefficients. The coefficients of the models. The size of the relationships must be all over the place for the IPCC models, and we can see a brief summary in that note on the bottom left. But let's go to the next chart here, next page here, and have a look at those parameters in more detail. So we're comparing models estimated using 1850 to 1933 data versus the models estimated using odd years of data. And in the top block, where we're forecasting all land temperatures using IPCC models, because that's what they've been set up to forecast, all land temperatures. They don't allow for urban heat islands. We see that the coefficients vary enormously between the 1850 to 1933 estimated models and the odd year estimated models. Particularly when we look at IPCC solar, there, the third line of numbers, if we use the 1850 to 1933 model, we would assume that more solar irradiance led to lower temperatures and vice versa, a negative relationship between the amount of energy from the sun and how warm the Earth is. Very strange. But if we estimate using odd years of data, we end up with a slightly positive relationship. Well, at least that's in the right direction. None of the other models have different directional estimates of relationships depending on what set of the data we use. But if we have a look at even the volcanic variable in the top block when we're estimating the IPCC models with volcanic in it for all land, if we use the 1850 to 1933 data, we've got a figure of 0.08. And if we use the odd years, it's only 0.03. Well, that's a pretty big difference. It's a small coefficient, but a pretty big difference. But go down to the rural land independent temperatures forecast with the independent models, and we see that the volcanic coefficient is pretty consistent with between the two independent models, around that 0.111 through to 0.15, and it doesn't change much whether we estimate the model with 1850 to 1933 and we're odd years. So this is what we expect, and the solar coefficients do vary somewhat, but they're in the same direction, and they're not as dramatic a change as the anthro models in the top block. So go back up to them, and we find that the anthro variable, which is their major causal variable, more than halves, depending on, or more than doubles, put it another way around, depending on which set of data that you use. Very strange behaviour when you're proposing causal models. Okay, let's summarise. So errors from the IPCC anthro, the CO2 models, were as large as 4 degrees Celsius for northern hemisphere all land in the tests that we did, and as large as 20 degrees Celsius for northern hemisphere rural in the tests that we did. The independent solar model forecasts were much less than 1 degree centigrade for all land. Mostly they were much less, and they were almost always much less than 1 degree centigrade when we were forecasting the rural temperatures. The errors from predicting that the future or out of sample errors would be equal to the median of the estimation sample errors, often much smaller than the IPCC anthro series model errors, and they were rarely that much larger than the independent solar model errors. Okay, they all performed as you'd expect. The IPCC models, on the other hand, were also unreliable. The estimates of the relationship between anthro and temperature varied enormously depending on which estimation sample we used. And as we've just discussed, we end up with a crazy situation where higher values of the IPCC solar irradiation variable were associated with lower temperatures when we used one but large block, one half of the data to estimate the relationship. Okay, conclusions. The anthropogenic models, the IPCC models, fail to provide evidence of man-made global warming. They fail to provide evidence of man-made global warming. That's a big statement. Unpredictable and uncontrollable variations in solar radiation and in volcanic eruptions are going to continue to determine changes in the Earth's climate. That's not going to change. It hasn't changed. It's not going to. And finally, if we try to deny that in our politics and our policies, if we try to deny that reality, we're going to continue to impose enormous punitive costs and intergenerational damage to our lifestyles, our livelihoods, our economies, how we live our lives, to almost everyone, and poor people in particular, and to what? To the benefit of very, very few people. What can I say?
Slide number 7. Let's put that one up because it really stands out to me. I put it up on Twitter already, actually. Yeah, so that one really jumps out because it shows anthropogenic forcing as being a net a little bit negative. It's in the blue there up until after 1950. That's what it's showing?
Yeah, look, it's it's relative to an average, So
yeah,
we're likely. I think the way those series are constructed is that there's going to be some kind of historical balance between above and below the zero line, but above and below the some average level, right?
Okay,
and that average in the case of the anthro variable, it hits 1970 and it just all of a sudden explodes. So more it's the bigger picture there to me is there's nothing happens before 1970. Well, that seems a little bit incredible given what we know about the industrial history of the last couple of hundred years.
Yeah, exactly. So I was wondering how that fits with the narrative that we've heard so many times that we know humans must have caused the warming since 1850 because that's when we started burning fossil fuels. And that's when there's a quote here I want to read from warmist Marshall Shepard. He actually said, quote, "After 1850, temperature went through the roof in warming, relatively speaking." So given the forcing we're seeing here, why would temperatures go through the roof from what we did? It makes no sense. Am I right?
You're right.
Okay, and then the whole thing about solar forcing being just nothing compared to anthroforcing, especially after 1970. There's no one that really studies the solar variations that believes that is close to the truth. Is that right?
That you would have to talk to Willie about, but clearly the variable, the solar variable that the IPCC chose, one of 28. Is the lowest or almost the lowest variation, variable, So, why?
Okay.
Why?
I'm curious as to who else.
If you're not sure, Tom, if scientists aren't sure which one is the most the best representation of the particular variable, then you'd start to look at taking averages. You'd start to look at testing alternatives as we've done here, and the predictive validity of the alternatives.
Okay, and then you wrote a book with the late J. Scott Armstrong. It sounds like you worked with him quite a bit in the past. Who else are you working with now besides Willie Soon? Any other people that we know?
Look, I'm in touch with most of the global warming skeptic people. I have done. You're right. I've done most of my work over the last 20 years with Scott and various others. Mostly I'm on my own. As the last standing scientific forecasting person looking at climate, I'm very pleased to be able to work with Willie, collaborate with Willie, because one of the key ideas of science and scientific forecasting is you work with the domain experts, and this is something that is, I think, underestimated by scientists in all kinds of fields, is that there is a domain expertise in forecasting. So you need both. If you're going to make predictions or even just testing a scientific hypothesis, and thinking about predictive validity and how you test that, and how you what your alternative hypotheses should look like, benefits enormously from the lessons we've learned in scientific forecasting.
Is there any sort of movement of younger scientists, people in college even, learning these principles, or that's not happening much now?
Forecasting principles?
Yeah.
Or scientific principles? Well,
yeah.
Tom, we've got to look at the motivations in in the academic world, and what are the key drivers for academics in order to get promotion and survive in that world, is to get publications in high status journals. It's to get big government grants, essentially. And as we write in as Scott and I wrote in the scientific method book that you can see behind me in the image, what the biggest enemy of the scientific method is government grants. Monopoly. As an economist by background, I mean, the monopolies are regarded as a bad thing. Governments don't like monopolies unless it's them. Well, that's exactly what's going on in the scientific world, is that the government funding of scientific research dominates the field to the extent that it's an effective monopoly. If you want to publish something that goes against government policy desired outcomes, then you're in trouble. The history of the publication of the paper that we're looking at here is a pretty sorry story of submitting it to the obvious journals, the high status journals that should be publishing it, and a lot of desk rejections on very on non-existent grounds, really, and getting to an extended review process that took months and months and months, only to get back really empty reviews. So neither the desk rejections nor the reviews actually addressed anything substantive about our paper. They did not engage with what we'd done. They could find no substantive reason for objection, and yet they declined to publish it. And so we're very grateful to the Science of Climate Change journal, People, for publishing our paper, because I think it's a really important one. I think it makes some very strong demonstrations that the causal arguments about man-made warming just do not hold water.
Do you think there is any growing realization that science is broken, and people have looked at what happened with COVID, and that's waking people up, and maybe science can get back on the rails in the upcoming decades? Do you hold out hope there that that could happen?
So if I were to paraphrase you, so you're saying, do you think the COVID reaction is well, the whole reaction to COVID, the public statements, the roles of governments, really, I think, further undermined the confidence of the general public in what's going on in science. What Scott and I wrote about in the scientific method book behind me is the corruption of government grants. We call it the advocacy research as opposed to scientific research. So much of what we see going on under the guise of science is advocacy research. It's research that's intended to deliver a particular result. And as with the IPCC, that's in their brief. They were given the intended result, which was to find a man-made influence on climate. Well, of course they found it, and the bigger the effect they could find, the more drama they could find, the more money they could extract in terms of grants and professorships and paper publications and so on. So the motivations are really, really bad, and the public are to some extent beginning to twig to that. I hope, but what does that mean? How do we know what to believe or trust that comes out of the scientific community anymore? And that's perhaps even more the case when we talk about health related things, as the COVID virus was, because it very much brings it home to people when other research may be a little bit abstract or a bit difficult to relate to people's day-to-day concerns. But here we go. We hope that the reality of ballooning energy costs, failures in the electricity grid and so on will start to bring that home to voters, to ordinary people. What is the solution, Tom? Well, the only long-term solution I can see is to get government out of scientific research, and that will eliminate a major motivation for advocacy research. Let's go back to the conclusions. I mean, this has been a crazy time, Tom, that's been going on far too long. When it should have been obvious to anyone who's been thinking about it at all, and looking out the window, that the claims, the crazy claims that are being made, just don't hold water. Sea level rises, extreme, weather, and our poor, children, grandchildren, and the people without a benefit of much scientific education are being scared silly. As people have discussed before, I'm not the first. I mean, it's a form of child abuse what our kids are being put through. I don't know how to what extent it's the case in the US, but in the schooling system here, it's part of deeply embedded in every aspect of the curriculum. These myths, this unscientific advocacy, it's broken a lot of relationships for me, Tom, over the years. I've had to, once I got started in this, I found people I'd thought of as friends, intelligent, educated people, have, I can't talk to them, or I don't talk to them. I don't, they don't want to talk to me anymore. They don't want to hear. They don't want to listen. They'd rather listen to, someone on the public radio or public TV channel.
I'm definitely sorry to hear that, but time will prove you correct, or already has proven you correct. So there's that.
Thank you, Tom. And then let's hope it's all over. The great Julian Simon, the economist, had the Simon Earl bet. He predicted that this would come to an end in the not too distant future, as all others have done, all the other alarms. And this is something Scott and I looked at. Some considerable years ago, and never published, but for the kinds of reasons that I've discussed, and it just became too much trouble. But we looked at the idea of that this is a political movement. So how do you forecast a political movement? And so we used a method that I developed of analogies, structured analogies analysis, and looked for analogous climate alarms, analogous environmentalist alarms, and we're very surprised at our own ignorance, I suppose, and identified as many as was it 27, I think, analogous environmentalist alarms, going back to the 1700s or so. That have all turned out to be based on unscientific forecasting, that the forecasts were all wrong, either in direction. The effects were either opposite to what was predicted, or they were trivial, non-important. But all of them resulted in harmful government policies, almost all of them. And almost all of them, those policies hung around, and most of us don't know that those environmentalist alarms were actually found to be wrong. They just drift out of consciousness. DDT and cancer is one of them, for example, perhaps the most dramatic. It's led to tens of millions of deaths from malaria by the banning of cancer. Banning of DDT.
Do you think this one is going to end just with a whimper too, that people will just stop talking about it rather than some dramatic admission that everything was wrong?
Well, I unfortunately, that's what the analogies suggest, Tom. It really is. I mean, can you see any sign that anyone will be punished, held to account, exposed over COVID?
No.
Can you see any Nobel Prizes being withdrawn for the so-called climate research? Papers detracted. I can't see it, unfortunately. I think people will go quietly away to their very comfortable retirements after having built careers on it. Unfortunately, I haven't got a more positive one on that. But I desperately hope that the worst of it the net zero, the policies that are promoting unreliable, costly, environmentally harmful forms of energy generation, electricity generation, are going to end soon, Tom, because they're just so bad.
I 100% agree. All right, I will let you go, but Kesten Green, thanks a lot for all you do, and keep it up. I appreciate it.
Thank you, Tom. It's been a pleasure.